UPS store is in front of you. Albertsons is in front of you. UPS store is close to you. Albertsons is close to you. No building nearby.
Hello everyone, we are IntelliSight and our project is Environment Awareness for Low Vision Patients. The IntelliSight team is made up of Rafael, who is in charge of the camera software integration, myself, Vanessa Mejia, and I was in charge of the PCB and map design, and Zinwan, who was in charge of the IMU software integration. When we are out in the world, we are able to understand our surroundings by using both our global and local context. Our global context refers to where we are in the world, things such as what street we're on or what city we're in. Our local context refers to what objects are in our surrounding environment, things such as how many cars or people are directly in front of us. According to the World Health Organization, there are 285 million people, low vision individuals in the world. Many of these individuals face many disadvantages when acclimating to the environment around them. Although technology has helped them understand their global context, things such as where they are in the world, like I mentioned before, using GPS, they still have to rely heavily on their senses and on the people around them in order to understand their local context. Technology is still unable to help them understand what is in their surroundings in a quick and easy way. The solution. IntelliSight solves this problem by developing a pair of smart sunglasses that uses visual information from a camera, orientation information from an IMU, and location information using the phone's GPS. This is all combined and is able to relay an in-depth understanding of the user's surrounding. This information is sent over to the user's phone, and once on the user's phone, our application combines this information and uses computer vision as well as maps information in order to identify the buildings and the objects directly around the user. For example, if the user is standing on the left-hand side of this image, our system is able to relay back to the user that they are standing directly in front of the UPS store. Moving on to hardware. Here we have our block diagram, which shows how everything works together. We start off with our LiPo battery, which powers our PCB, and our power boost takes the 3.7 volts from this battery and is able to output 5 volts in order to power our camera. Our camera is connected to our microcontroller using SPI, and our IMU sensor is connected using I2C. Our microcontroller is able to gather both the information from the camera and the IMU sensor and send it over to the phone using Bluetooth. On the phone, we are able to process this information using our application and then send the relevant information back to the user's headphones using Bluetooth as well. When we were designing this project, we knew that we wanted it to be hands-free, which is why we decided to use the ESP32 as our microcontroller, due to the fact that it has integrated Wi-Fi and Bluetooth modules. The ESP32 interfaces our camera and our IMU sensor. It takes this data and sends it over to the phone using Bluetooth, and it also has an onboard USB to serial converter. The operating voltage for our ESP32 is 3.7 volts. For data collection, we use both an IMU and a camera. The inertial measurement unit we decided to use was the BNO055. This device collects the user's orientation data and is also able to capture the user's gestures, things such as a head nod. The operating voltage for this device is 3.3 volts, and it is interfaced to our ESP32 using I2C. The camera we chose was the Articam Mini 2MP, and we use this when the user wants to know what is in their surrounding environment. They're able to snap a quick picture with our camera. The operating voltage for this device is 5 volts, and it is interfaced with our ESP32 using SPI. For power supply, we had a LiPo battery, which has an operating voltage of 3.7 volts, and this is what powers the PCB. We also have a PowerBoost 500C, and this takes the 3.7 volts as an input and is able to output 5 volts in order to power our camera. Moving on to our printed circuit board. This is our PCB schematic, and we have our power boost, our microcontroller, our IMU, and our camera header pins all on our PCB. This is our PCB layout. We wanted to keep it as small as possible in order for it to fit nicely on the user's sunglasses. And so this is why it is 2.67 inches in length and 1.15 inches in width. And it is made up of 4 layers. This is a picture of our final PCB. Moving on to software. For software, we have 2 different modes. We have the first mode, which is camera mode, and this has object detection. Mode is our IMU mode, which has gesture and building detection, and it also has text-to-speech. Moving on to camera mode. In camera mode, the users are able to take pictures of their surrounding environment when they want to know what objects are directly near them. Our camera is able to send this picture to our ESP32 using SPI, and then from our ESP32 to our phone using Bluetooth. Once we are on our phone, our application is able to identify the objects in the pictures using TensorFlow Lite, and then we relay the relevant information back to the user using text-to-speech. The users are now able to have a good understanding of what objects are in their surrounding environment. Moving on to IMU mode, I'll let Xinhuang take it away.
Hi everyone, I'm Xinyuan, and I will give you guys more detail about our IMU mode and also our final product. And first, let's look at what happened for our IMU mode. So here is a picture, and first of all, here is the IMU sensor like we used to detect user's gesture, and it's set on the side of our sunglasses, so it's easy to capture the motion for user's head. And then once we detect the desired gesture, it will switch to collect bearing data, and then the data will sent to the microcontroller, and the microcontroller will transmit the bearing data to our app via the Bluetooth attached on the microcontroller. And then as our app receives the bearing data, and also based on the user's GPS location, it will start to scan along the bearing to detect the landmark. And finally, the results will return in voice. Next, let's talk about what happened on nodding. And let's look at this graph first. As you can see, this white square is the IMU chip. And for the gesture like we detect, what it really happened is to let the chip rotate along the y-axis. So we can see like as pitch. And here is and for the vertical line is a value for the pitch, and as the people move their head up and lower, and the value of pitch will change as the time passed. So what we do is like, as you can see, the yellow line is a trace for the nodding, and if we detect there's a negative pitch value lower than some threshold that we set it here, and then we will start to collect the pitch value for the following several seconds and find the highest value, and then we will get the difference between these two. we call this difference value. And then we will get the threshold to compare. If it's larger or equal to the threshold, like we set it, we will say, okay, it's our IMU mode being triggered. And next, let's talk more about our gesture detection. First of all, let's look at the table here. This table is about the operating modes for our sensor. And here are so many modes, but what we pick is the 9 degree of freedom mode, because it's okay to receive the sensor signals about the oscillometer, magnetometer, gyroscope, and the absolute orientation. So it allows us to detect the user's gesture and at the same time able to get the accurate compass data for the following step. And next, let's talk about the data like we receive. Like the type of compass data we use is azimuth. So you can see the inner circle of this circle, like it uses the number from 0 to 630 degree to represent the direction. So it's easy for us to process the data for the following step. Next, let's talk more about building detection. On the app set, so as you can see here, this spot represents the user's location, and once we get the bearing data, it will start to search along the bearing data by first move 2 meters to do the first search, and if we find there are any landmark in such a range, we will directly return the results. However, most of the time, like the building search will fail. So we will continue move along the bearing data to do the further search, something like this. And if we find any results, it will be returned. But if it didn't, like it will continue to do the further search. And if we find like we still couldn't find any results 80 meters away from user's location, and we will return some other results. So let's talk more about what's the value being returned. And first of all, as I mentioned, like all our final result is returned in voice. And let's look at the picture. This is how the return looks like on the map view. And let's show how the value returned. If the landmark is within less than 30 meters away from the user, it will return like X is in front of you. If the building we detected is 30 to 80 meters away from the user, it will say X is close to you. And if the landmark is 80 meters away, like out of our detected range, it will return like no building nearby. And yes, that's how the value being returned. And next, let's say our further development is currently our IMU mode is okay to use, but we still have 2 aspects like words to get the better, able to improve to get better results. One is a compass accuracy. What I refer to is like if the user do some actions such as jumping, shaking head or running some crazy motion, and then to try to get the compass data. Most of the time, our compass data may not be that accuracy than the Euro. So we will try to consider some solution. Yeah, we will try to find some solution to make the compass keep accurate, even when after some like crazy action. And next is to get a better state estimation. What happen is like when we do some certain search, we might find there are more than 1 landmarks in our certain search. So we need to use more parameters that we get from the JSON package to better decide which one has a higher possibility, like is a building like really in front of the user, to make our results more accurate. Next, let me show you guys our final product. So this is how our final product look like, and we will include all our chips in the black box, and the black box will attach on the side of any sunglasses, and because it can easily remove and also it's very light, so it's okay to take out or or like just view the sunglasses as URL. And on the left side, on the right side, this is how our app look like as we successfully Bluetooth impaired, and it will return some data about what mode right now, and also relative data, something like bearing data. And finally, it will return the results, I mean the user's position and the detected landmark on our map on the center. And here is it. Now let's see a demo. So what happened, like, or how do we really view it and use it?
UPS store is in front of you. Albertsons is in front of you. UPS store is close to you. Albertsons is close to you. No building nearby.
So that's it. And okay. Previous. Thanks for the Professor Yoga, TA Adi, TA Kyle, and the support from Qualum, and thank you very much. And any questions? Anybody?
Did you have any issues with false positives while you were trying to nod your head, like when you're walking or anything? And how did you fix it?
Wait, well, can you repeat the first sentence?
Did you have any issues with false positives, like like the glasses thinking you're nodding your head when it wasn't, when you weren't?
Do you mean like any problem on detecting the nod gesture?
Yes.
Oh, something is like, cause let me think how to say that. Oh, sometimes it's like when people try to finish their nods, but they spend like they are too slow or too quick. So at this moment, we couldn't successfully, we couldn't like really calculate. We couldn't, if it's too slow, like we couldn't get the high value higher enough. So like we will consider this difference is not, it is smaller than a threshold. So it will not be considered as the gesture we want. But if the user like they nodding like too quickly, so because like as I mentioned, like after I detect the negative pitch value, I will start to collect and get and to figure out the high-res data. But the data like we're collecting at that moment is based on some like time with some time step. So like if you nod your head too quickly, so maybe we will lose to capture that higher value, I mean the highest value we want to get. And that moment we will find like, oh, seems the threshold is not high, the difference we get is not high enough, and then it will be considered as, okay, it's not twice nodding. And also sometimes, because we set a negative value to start to collect the following data, but sometimes it's like, some people like they may like lower their head not that much, but they will hide their head like pretty much. But at this moment, the data may not be captured because like the users like lower their head, the value is not small enough. So it will not be considered as start to nod. So even will not get the difference to consider whether it's nodding or not. So this is some problem like we met when we try to measure the nodding head. Yeah.